So thin film interference is when an incident wave's reflection from the front of the film interferes with its reflection from the back of the film. And this is why when you look at like soap bubbles, they look colorful. This is why it takes me like, hours sometimes to do the dishes if I have good reflections, especially if I've got like a potato masher and I can get the bubbles on the potato masher and I can hold them up. And anyway, and also why oil films have colors on them. Okay, and that's because those colors are constructively interfering. Okay, now let me explain the how this happens. Right, interference happens whenever you have different path lengths. So if you look at the black line there, light rays coming in could reflect off the front surface and then just come back. That's what that black arrow represents. But some of the light is also going through the film, reflecting off the back side and coming up. Okay, that light has actually traveled a farther distance, right? A greater distance, and so therefore is slightly out of phase, right? Okay, and so when you look at it like this, you're going to see light that traveled this distance and light that traveled this distance, okay? And that can cause constructive and destructive interference. Now, normally we think that the 1/2 is associated with destructive interference. Here's why it's not in this case. Okay, let's look at destructive interference, okay? Let's imagine that our thickness gets very, very small and that the integer that we use here is a 0. Okay, so the film is, say the wavelength of light is 400 nanometers, a very short wavelength. Well, if the film is like, say a nanometer thick or something like that, it's essentially nothing compared to 400, right? Okay, so if we look at this, we make this thin film very, very thin, okay? The reason why you'd get destructive interference with a totally thin film is that what happens here is this, since it's a higher index of refraction, it's slower, it's more dense. And so the reflection off of this side here is actually inverted, right? And so essentially they would have traveled the same distance, right? But one wave would be inverted, the other would not be inverted. And that's exactly how you cancel out sound or light or anything like that. You superpose a crest with a trough, okay? So understand that this first interface inverts. The second one doesn't though, because this reflection here occurs between the more dense medium and some less dense medium, okay? And so that's an upright reflection, okay? And that's why the destructive interference actually has the integer number of wavelengths. And the constructive interference, you need to get constructive, you need to have another half wavelength shift so that you're not superposing an inverted wave with a upright wave, okay? It's the fact that this interface here actually inverts, okay? Now, where do these formulas come from? It's not that hard to figure out. Remember that the lambda, if this is lambda here, right? Oh, by the way, this only works if this index of refraction is 1, and then this, let's say this is, I don't know, 1.33 because it's water or something like that, right? Okay. Remember that the lambda in here is just lambda divided by n, right? And so really what we're doing here, and then notice that the wave travels into the thing and back out, right? So it actually travels 2D. So if 2D is equal to some integer plus 1/2, because you have to account for that phase shift, right? Okay, times lambda over n. This lambda over n is what the wavelength is inside this medium, okay? If you recall that from refraction, okay? Then you get this formula. It makes sense, right? The difference in distance is that you have to go into the medium and out of the medium, right? That's our difference in distance. And then that equals this. And the reason there's a 1/2 there is because of that inversion that happens at this first boundary right there, okay? Let's take a look at the colors that you get, right? This is kind of fun. This is my favorite one right here, is this pattern that you see. And this is not random. This is a vertically oriented soap bubble. If you look at this top region where it's black, that's where it's so thin that it's not constructively interfering any visible light. And then you get kind of this muddy look like that, right? So when you look at bubbles, if you pay attention to bubbles, bubbles will get these colors on them. But when they start to look kind of muddy and brown like that, that's right before they pop. I spent a lot of time looking at bubbles as a kid because I found them fascinating, right? And what that means is that the bubble is getting thinner and thinner and thinner, right? At some point it does pop, okay? And that's that sort of muddy brown color. Now, if you look at this, let's look at the green, right? The interference of green. It interferes here, it interferes here. So this is m equals 0, m equals 1, m equals 2, m equals 3, m equals 4. So this soap bubble is getting thicker and thicker and thicker at the bottom, right? with that formula, right? That's what's going on here. The reason it's going through all the Roy G. Bivs is that that M in that formula is an integer. It's just going through all the numbers, right? This is just oil. It's pretty. This is the oil drop here, thicker, thinner, right? And then bubbles, of course, have these on them like that. Okay. All right.